Right now we have a great talk. This was the highest ranked talk in our review process. It is Boot Security in the MCU by Zoltan, Madarassy and Daniel. Let's welcome them to the stage.
Thank you. Yeah, let's just jump straight in. So, who are we? This is my colleague and friend Dan, also known as the Bald One. And he's a co-founder at Altam and also a principal consultant there. He's been auditing code for over 2 decades and just loves reading like anything related to like systems and firmware in the systems and firmware space. And I am Zoltan. I'm also a principal consultant at Altam, and I've always struggled with keeping my toys and gadgets functioning because of just the strong urge to understand how things work. And what we are going to talk about today is boot security in the MCU, as the title also said. If you came in expecting us to talk about like the suit of Iron Man or anything like how it works, I will have to disappoint you. But we are going to talk about microcontrollers, the other MCU, the OG MCU, especially ESP32 and STM32 as the 2 biggest vendors that we've looked at, and their secure boot reference implementations, basically. And we are going to do this talk also highlighting some of the collaboration things we've done to coordinate our research, hoping that it will be useful for anyone who wants to do any sort of similar things. So yeah, what are microcontrollers? I guess if you're here, you already have an idea, but just in case, essentially they are like small computers that has like a processor, could have built-in memory, peripherals, I/O. The combination of all of these can be like, you know, so vast depending on what the use case is for that particular microcontroller. And you can find them basically anywhere, like in your badges. Well, I guess not necessarily this year unless you soldered some on, but that last year's badges, or your watch if you have a smart watch, or even your AirPods have pretty powerful microcontrollers in them. Yeah, anywhere really, so it's pretty widespread nowadays. So it is important to focus on these kinds of topics, we believe. And following this, what is secure boot? Well, secure boot is what we're going to talk about today. But in a nutshell, it's basically aimed to protect the MCU from against running unverified code. It has basically 3 major strategies that secure boot implementations will want to sort of adhere to and achieve. One is protection, so protecting the code itself that's running on the MCU against malicious inputs and like malicious code. Also protecting the data that's on the device, so it has a privacy implication as well, and also like an intellectual property kind of side as well, so that the vendors who put these devices out on the market in the hands of their consumers can rest assured, can sleep safely knowing that their code is safe and no one's going to steal them, ideally. And it also has a detection kind of capability, so secure boot should also be used, or like should be able to detect if malicious activity is being performed against the device, so it can shut down or reset or things like that. And also recovery, so you know, in case there's some compromise or just not necessarily even like intentional, but something happens, the device can reset to a known secure and safe state. So these are all covered under secure boot. There's no real industry standard that everyone has to follow if they want to implement secure boot, but there's been some work in this area. So there are some NIST recommendations, there are some guidelines out there that try to sort of have some universal guidelines on how to implement secure boot, but there's nothing like a widely accepted standard just at the moment. So how does secure boot work? It starts with what is called a root of trust. So this is a piece of immutable secret that the whole process relies on to verify each next step in the boot chain. So this root of trust is usually just burnt into a device, potentially in the boot ROM, which is unchangeable most of the time, or some other secure area which is immutable and secured against malicious readouts or compromise. And the process works in a way that this root of trust is used by the boot ROM, which is the first step of the boot chain. So as I mentioned, the boot ROM is usually fixed in hardware, cannot be changed. So if there are bugs in here, then they are there. And the boot ROM will use this root of trust to verify the second stage bootloader, which is also immutable code but can be updated using the same secure boot process. And then the second stage bootloader, using the same certificate chain, usually will verify the application firmware, which is going to be performing what the device is supposed to be doing at the end of the day. And our focus when it comes to secure boot was not on the first stage bootloader, because there's been a lot of really good research out there. People so boot ROM code is not really public. Vendors try to keep that a bit of a secret, obviously, because if there's bugs in it or anything like that, they cannot update it unless in the next generation of the firmware, the hardware. So there's been a lot of really good research published on reversing boot ROM code and things like that, but we are not really focusing on that at this point. We are focusing on the second stage bootloader because at Altan we do a lot of code reviews and things like that. So we have a good amount of experience auditing code. So second stage bootloaders tend to be open source from some vendors, and they are what they are calling reference implementations. So they should not be used one-to-one in a production environment, but developers can use the reference implementation of the second stage bootloader to implement what they need to secure their devices. So we are focusing on this. The reason we are doing this is so we can demonstrate practical test cases against why these recommendations are out there. We can find bugs, submit them upstream so they get fixed even in current live production devices. And also as a business we can provide tailored guidance to our customers using these sort of secure bootloaders. And also we are not doing this because it's easy, but because we thought it would be easy. So that's a bit of a warm-up, and I will just pass it to Dan, who will talk about ESP32 now.
Okay, the ESP32 was the first microcontroller we chose to look at for several reasons we'll get into in a sec, but it turned out to be a great choice. The thing with the Espressif is it's a huge family of microcontrollers. There's a bunch of different series. Within each series, a whole lot of different microcontroller implementations. You kind of have to just pick one and use that as what you're going to look at. So in our case, we just chose one of the oldest versions of the ESP, which is most commonly deployed and has a lot of great research out there already. The ESP32 is essentially running the extensor LX6 architecture, which was sort of new for us. There are some documentation out there that you can read, but fortunately, focusing on the second stage bootloader, we get to focus mostly on source code, don't necessarily have to go too in-depth on the architecture. The security features that it offers is essentially a kilobyte of one-time programmable memory, and a hardware secure boot and flash encryption. Essentially, it's the thing in the picture there with the green square around it. The ESP IDF framework is basically the reference implementation that Espressif ships that developers can use to program these microcontrollers. It provides all sorts of components and different things that you would want to use, and just saves development time. And the reference implementation in that is what we were focusing on. We also chose many different versions or major versions of the framework just to get an understanding of how Secure Boot has evolved within that code base over time, so that we could develop different test cases depending on which version of the framework somebody's using. To basically get started in this, we need to do doc review, and fortunately for us, Espressif is fantastic in their documentation and their code. They basically open source everything. They've got really in-depth data sheets, technical reference manuals, guides on their website, as well as a really inclusive community with lots of fantastic forum posts. This was a fantastic place to start, since if you're getting into microcontrollers, having all this information readily accessible just gets you up to speed nice and quick. One of the things that we saw in there is Espressif do recommend that if you're running a production device, that you should enable Secure Boot. So it seems like a great attack surface and something that we should focus on. A lot of the documentation indicated that security is more or less controlled via these one-time programmable fuses. If you're not familiar with what these are, it's essentially an image on the screen here. The one on the left is a fuse that has not been burnt, and it represents the value 0. Fuses can be programmed via software, meaning that you can essentially issue instruction to the fuse controller, and the fuse controller will physically essentially damage the fuse, so burn it, and as a result of that, the value of that fuse will change. It'll go from a 0 to a 1, and you can see on the right, that's an example of a physically burnt fuse. Because it's physically burnt, it's not possible to roll back that operation, so once a fuse is set, it can never be unset. This is obviously a desirable property for security, so once you lock down a system, it's not like somebody can go in and reverse those operations. So the 1 kilobyte of one-time programmable memory is split into 4 blocks. Block 0 is what's called the system parameter block, and this block is really for locking down the microcontroller, setting features that should be enabled or disabled depending on a vendor's need. Block 1 is pretty much reserved to hold the flash encryption key. So if you're using flash encryption, this is where the secrets get stored. And block 2 is where the secure boot keys are burnt into memory as well. Block 3 is kind of for just application purposes, anything that you might need to do and make use of as a one-time operation is available for you to use in block 3. One of the properties that you find with eFuses is it's not sufficient to simply burn them or not burn them. You also want to have the ability to protect reading those fuses or writing to those fuses in certain cases. So a clear and easy to understand example would be the flash encryption key. That's a secret material that should never be exposed to anybody, since if you can access a flash encryption key, you can obviously decrypt the flash as well. So by read protecting that block, say block 1, it's possible to burn the key, and software cannot access it, but hardware can. The other operation that can occur is also write protection, so you don't necessarily have to burn a fuse. You can also leave it as the value 0 and write protect it, meaning that it's not allowed to be burnt. So a basic example would be when you receive an ESP microcontroller, generally comes with a MAC address, since they have like a Wi-Fi and a BLE stack, and the MAC address comes from the factory. It's often used as a way of uniquely identifying which chip you have. So if Zoltan's ESP32 connects to the internet, his MAC address would be different to my MAC address. The interesting thing is that there's no write protection on this memory, so we can obviously change the bits of that and change the factory MAC address, which is maybe not ideal. So obviously, if we're shipping a product that relies on MAC addresses, we need to write protect that memory. The real reason why we care about looking at these eFuses to begin with that documentation review, is we need to understand a little bit about the platform, since if we look at the reference implementation for Secure Boot, it's no good just focusing on that if the rest of the microcontroller remains in an insecure state. So spending a little bit of time learning about the different fuse configurations lets you determine what the recommended values should be. As a basic example, there's a fuse in the system parameter block called JTAG disable, and this might be used to disable JTAG in production, so that users can't simply attach their JTAG probes and peek and poke memory and do debug operations. You'd want to do this in the case of Secure Boot, because if it's not done, then obviously somebody could just inject their own code into the memory and bypass any guarantees that might otherwise provide. So with that out of the way, that was kind of like the doc review and initial experimentation. Just learning enough about the microcontroller to know what needs to be locked down. But really, since our focus is on the code auditing, let's assume that the microcontroller is configured according to best practices. Again, Espressif is great. They've got documentation on what those best practices are. And we also have a tool that we'll release at the end that you can use to verify that your code might be conformant. So our approach was basically audit all of the things. Really what that means is we pulled down the ESP IDF code base. There's two folders in there, one called bootloader, the other bootloader support. These are obviously related to bootloaders, and so our goal is just to read every bit of code that lives in that folder and try and find bugs. So what that kind of means is we start at the first entry point, which is called call start CPU 0. And you just read it line by line, try and build an understanding of what's happening, why certain operations might take place, and try and figure out different attack scenarios. And so this is literally only a few, this code block on the screen is only a few lines into that function. And what I've indicated here is there's a function called something called select partition number. So this means that we need to now understand a little bit about what a partition is and why it's selecting a partition number. So a few slides back you saw what a microcontroller is, and so it's obviously the ESP on the left. But the chip to the right of it is Spire Flash. It's external memory. It's physically a chip that lives separate to the ESP, but can hold data. You can think of it as like a hard disk or something in a traditional computer. So this flash memory just stores data, and it can be anything. The only constraints are that the first few kilobytes of that memory hold the second stage bootloader and a digest of it, which is used by the boot ROM to verify the bootloader. So from an attacker's point of view, or for our point of view, we can't really modify these things, so we just leave it as is. But the rest of that Spire Flash is for the taking. So the partition table is at some offset within this flash memory, and the partition table basically points to different sectors of the flash memory and says, maybe this partition is reserved for data, another one might hold an application code, another one might contain, like parameters for configuring hardware and so on. So, okay, we sort of understand that there's this external device now, contains data that we can modify. We then get a few lines lower and see a call to bootloader utility load boot image. Okay, so we jump into that function, and again, it's only a few lines in, and you hit something which says check anti-rollback. So the next thing to do is, okay, what's anti-rollback? Why do we care that it's actually making this function call? Again, go back to the documentation, learn a little bit about it. Essentially, anti-rollback is used in situations where the microcontroller receives a firmware update over the internet. It'll receive that update, it'll write it to another partition, an unused partition, and the requirement would be that the application, so the version of that firmware update, needs to be higher than the currently running version. And it's basically, the reason for anti-rollback is that you should be able to download an update that fixes a vulnerability, and the system should never be able to go back in time and run a known vulnerable version of the firmware that might still be signed. So the basic approach to it is, let's say that the current, so the code that's running in OTA 0 is the thing that's actually going out and speaking to the internet to get a firmware update. It downloads it, it then writes it to OTA 1, and then the next operation it does is it changes the active partition in this OTA data partition. Then on the next boot, rather than booting into the OTA 0, the microcontroller will boot into OTA 1, and then when OTA 1 successfully boots up, it'll blow an E-fuse, and that E-fuse is essentially an increment counter that represents the currently allowed version of the firmware to run. And because it's blowing an E-fuse, it means you can never roll back in time and run an older version. So the question then becomes, how do we know what version essentially a firmware is? And that basically comes down to the image format, the application image format, which sort of lives in one of those partitions. So in our case, this image header and segment array and so on will live in OTA 1. We don't really need to care too much about all the different structures in an application image format. For our purposes, we just care about this one structure, which is called an ESP app desk. It's the very first segment in the update image, and this contains a value called secure version, which is essentially that firmware's version that would be running. So, okay, that makes sense. We know what anti-rollback is, but then we see the next core, which is try-load partition, and we won't go through the code and the implementation of that, but it essentially loads the application and runs it. But we've already just learned enough about this behavior to realize that there's an issue here. If Spy Flash is under the control of an attacker, it's an external device, we could desolder it, we could solder on our own emulator, we have full control over it. We've seen that there's a moment in time in which the versioning information is checked, and then a moment in time in which the firmware is actually loaded and executed. This is essentially indicative of an issue called timer check, timer use, where if we replace the data that's being used at these two different times, then we'll end up being able to potentially changing a secure version from some higher value to a lower value and running that. So we've got a theory of where an issue kind of exists. How would we test this on, in practice? Fortunately, ESP has QEMU support, and so you can emulate the microcontroller itself. And one of the nice things with this is that Spy Flash memory can be pointed to a fake block device. And in our case, we used something called NBD kit, which lets you essentially turn a file from your file system or some program into a fake block device. And our goal here is our NBD kit is just a program, and when a fetch occurs to, say, OTA 1, we'll return the valid firmware update. But then the very next time we see an access to that OTA 1 petition, we'll return some older version of the firmware that has a vulnerability in it. And turns out that that theory was a great success, and got the first CVE from our work. So shout outs to Joseph for the initial finding. And what you see in the screenshot up the top is a secure boot version saying that in the eFuses, the firmware update must be version 10. You're not allowed to run any version less than that. But then down below you see that the actual running version of this firmware is actually version 0. Might have a vulnerability in it that we can now exploit, get control over the device. So that was pretty nice. And this whole idea of accesses to Flash and the time in which something's loaded, the time in which it might be used, seems pretty interesting. And the MBD kit integration is kind of powerful enough that we can actually start logging which sector of Flash is being accessed, at what time, whether it's a read or a write operation, and then you can plot that over time. And so we wrote a little bit of tooling just to sort of see how common this sort of double fetch case is. And as you can see in the GIF on the screen, it seems to be pretty common. There's a lot of cases in which the same region of Flash memory is accessed over and over again. This tooling has also been extended to support logic analyzer plugins, so you can do this on physical hardware, not just in an emulated environment, and see what's actually happening in practice. So that tooling kind of helped us a lot. And continuing on with this time of check, time of use issue, we kept auditing the code, just as you saw before, line by line, see a feature, go research it in the docs, come back and think about if there's an attack scenario. And we end up in this function called process segment data. This is probably like the holy grail of issues if you find a vulnerability in this function. It's actually responsible for loading the data like an application from Flash into RAM, and at the same time computing the hash of it for secure boot verification. So the idea being all the data that gets loaded into RAM, at the very end of that load, it'll then compare the checksums, and if it's allowed to execute, then it will. If not, then it'll bail out. But you see this sort of primitive, the two lines with the arrows. The very first one, you see this access to the variable src at index wi. And then that's actually the first operation where it fetches the data and loads it into RAM. The second time you see it with the second arrow down below, it's accessing src wi again, but this time for the purpose of figuring out or essentially using it in the hash calculation. So this is pretty nasty, knowing already that we can just toggle between which data is being received from Flash. We now have a case where the data that's loaded into RAM can be different to the data which is having the secure boot verification done on it. That seemed pretty awesome, except it turns out that caching is a thing on the ESP, and the access granularity was, or the locality of the accesses was too close, and as a result, those two fetches, it would not always go back out to the spy flash. It would actually just use whatever was left over in cache. And as a result, even though technically there's a time of use issue in code, in practice, the behavior of the hardware and this caching mechanism means that it turned out that it wasn't exploitable. One of my ideas at the moment, though, is Espressif are not just running on the Extensor LX6. There's also an LX7 architecture. There's a RISC-V architecture. I don't know if there's even more than that. But I wouldn't be surprised if there's situations in which this caching mechanism works different, and therefore, because it's the one code base that's used for all these devices, all of a sudden that vulnerability might become exploitable in practice. So fingers crossed that that leads to something interesting soon. But yeah, so I could basically talk all day on ASP issues and all the different things that you can do. Our research is far from complete with it, but the too long didn't read is basically time of check, time of use. Seems like a very powerful, primitive and juicy attack surface. Otherwise, the rest of the boot flow that we were looking at in terms of attack surface and ways in which we could tamper with the system to potentially get a bypass, it actually seemed pretty good on first pass. Again, there seems to be an opportunity for esoteric issues since it's one code base running on many different architectures. Maybe there's different quirks that happen there. This is an area that I'm still exploring. But overall, I think if you're interested in the topic of secure boot, ESP32 seems like a great choice of microcontroller, thanks to the documentation, the forums, and the code is quite clean, and the ability to emulate it. So I think I'll pass over to Zoltan for the SDM side.
Thanks. So yeah, switching gears a little bit here, we are going to switch over to another vendor that is similarly pretty widespread in the embedded space. ST Microelectronics is STM32 family of MCUs. As I said, similar to ESP32, there's a lot of different versions of their chips out there. So just if you go on their website, they have this nice little diagram, which is the main family of their MCUs. So as you can see, there's the F series, there's the H series, G, L, etc., etc. But if you go to their module selector table thingy, you can see that they actually have about 2,000 different MCUs that support secure boot and secure install and update functionality. And all of these will belong to these larger families, but in different configurations with different peripherals, different CPU speeds, energy consumption, etc. Whatever you need to fit your purposes, you will find it with STM32 if you can find it. Because when we started doing the documentation review, compared to ESP32, which Dan was really enjoying and just had a really good time reading through ESP docs and just forum posts and stuff like that, when I was doing STM32, I felt like I was in Dante's 9 Circles of Hell, especially somewhere between Circle 5 and 7, which is like anger, heresy, and violence, because STM's documentation is all over the place. Their websites are just contradicting sometimes. It's really hard to find actual usable technical documentations hidden inside their trainings and things like that. They do have really good data sheets. I will have to give it to them. Memory layouts are easy to find in those 1,200 pages of PDFs. But overall, it's kind of hard to figure out the STM ecosystem. And on top of this, their source versioning is not versioning. They bundle different source bases together, so it's really hard to find what you want consistently. But for our purposes, we focused on the STM32L4S5. It's a really catchy name. And specifically the discovery kits that is B-L4S5-IoT01A. Again, great naming. So the reason we chose this is because this is a pretty cheap MCU, pretty widespread. It's a low-powered MCU. It doesn't necessarily have the highest security sort of features or the highest power that STM offers, but it is very accessible and used in a lot of places. So it has, a bit of RAM, a bit of flash support, and all the communication interfaces and peripherals that you would need to interact with the device. And when it comes to their firmware support, just how ESP has the IDF framework, STM at the time had mainly support for what they call X-Cube SBSFU. SBSFU stands for Secure Boot and Secure Firmware Update. But as I was putting together these slides, the research I think we did it last year, basically. So there's been a bit of a gap in time between the actual research and the slides, and I was just working on the slides when I saw that they actually support 2 new things, or at least they are more pronounced now. They might have supported it, but I just couldn't find it in documentation. So they also support SBSFU by MCU boot, which was not available during our research, but it seems to be the main thing that they will be supporting from now on. On the screenshot, you can see that it's coming soon. So great. But yeah, we were focusing on SBSFU at the time. So SBSFU's documentation, again, when you're jumping into auditing something that is so complex and big, you start with doc reviews. They had a nice little strategy outline for how they do secure boot and firmware updates. So these are the strategies that they will adhere to. Single code of entry, single code entry is the SBSFU binary itself. So this is the immutable code that will be used throughout the whole secure boot process. They rely on ARM features, security features. So ARM is the architecture that they're using for their MCUs. Mainly they're relying on RDP, which is called readout protection. We will get back to that in a second. And they also have this strategy to protect and isolate secrets in enclaves. So this can be either in the flash itself, in a protected region that's immutable and protected against unauthorized access, or it can be stored in an external secure element called the ST safe, which is another family of MCUs that ST has. We'll get back to that in a second as well. And they also want to limit the SBSFU attack surface, so only support what they really need to support. And of course, disable all debug ports, but mainly JTAG or SWD or whatever when RDP is enabled, in order to limit access to the runtime, basically, or the instructions that are running on the chip during secure boot. And they also have this strategy of monitoring the system against tampering, so they have all sorts of security features that they use from ARM related to temperature control and all sorts of side channel monitoring capabilities. But the common element seems to be the RDP security feature. So this comes from the ARM architecture. RDP has 2 levels. 0 to 2, 3 levels, 0 to 2, and they are, it's just one of the security features that ARM support, but it is the main one. So depending on depending on the use case that developers want to build their environment around, they can use multiple other features as well, such as the memory protection unit, which can mark memory pages with granular access controls. So you can mark memory pages as non-executable, or just read-only, or read-write, etc., etc. Another common feature is write protection, WRP, which will protect the marked regions against erasing and reprogramming in memory. There's also PCR-OP, which is proprietary code readout protection, which protects again, you can mark memory pages to be execute only, and there's also a firewall, which is basically in ARM you can have multiple levels of code execution. You can have unprivileged code and privileged code, and the firewall is used basically to ensure that privileged code can only be called from privileged code, and protect against these sorts of attacks. And there's a bunch more other security features that ARM support. These are just the main ones that are shared across the STM family of chips most of the time. But even then, some might have less support, some might have more. And it's contrary to Espressif ESP32, these features are encoded in flash in the option bytes. On the screenshot, we can see the memory layout of the L4 series of chips, and those option bytes are what will dictate how these security features are used and whether they are enabled or not. And these are immutable and are protected at the end of the day by RDP. So RDP, as I mentioned, has 3 levels. RDP level 1 is just no protection at all. Flash and the RAM, or the memory of the chip can be read using a debugger. There's nothing stopping anyone from messing with the boot flow or anything like that using a debugger. Level 1 is a bit more protection. So in case of a debugger being attached to the device, if RDP level 1 is set, the device will halt, and the reference implementation will also reset the device. So it's a bit more protection, but because the device will halt when it detects a debugger, the RAM contents will still be accessible to the debugger. So if there are secrets still in RAM when the debugger is attached during the boot flow, those can be read. So it's not great, but it is a step up from no protection at all. And it has to be noted that level 1 can be downgraded to level 0. The SBSFU code, the reference implementation by ST, at this point will reset the chip, so deleting all data that is stored there. So there's a bit of rollback protection there. Yeah, still RDP level 1 can be downgraded to level 0 programmatically. That's like allowed in the documentation as well. And then level 2 is the one that is truly immutable. Once this is set, no access will be allowed to either RAM or the flash, and this is the level of lockdown that people should aim for if they are developing their own devices. It is a bit of because ST offers level 1, some vendors tend to choose that because they think that they might want to do some field debugging or whatever that they want to do, but it's usually not worth it for the risk of the lax security controls compared to level 2. But if level 2 is set, there is no debugging basically on the chip. So in the flash, that little table shows the option bytes that correspond to the level of protection of readout, like RDP, the readout protection bits. So hex CC in the RDP option byte part will mean that it's level 2. Hex AA will mean it's no protection at all, and anything that's not either AA or CC will be level 1. So that's a bit of an interesting attack surface there. There's been some research published with related to using strong UV lights, just shining on the MCU, which can cause bit flips, where they can basically downgrade the level 2 to level 1 by flipping just one bit, so that the hex CC becomes not hex CC, but also not AA necessarily. So it will just be a downgrade to level 1. However, that sort of attack is unreliable because at the time when I was putting together the research, there was no specific enough UV attack that didn't also corrupt other parts of the chip. So even data that you would be after with this attack would be corrupted. So it kind of makes it unfeasible. And then there's a lot of research out there using fault injection to sort of just skip over these sort of checks and bypass readout protection. But these are all hardware-related attacks, which is not our focus. So we started looking at the SBSFU code. How it's organized is it's organized. So basically, they always have two versions of the SBSFU codes broken down into different chips that they support or discovery kits that they support. There's a KMS version, which is, as I mentioned, relates to how the secrets are stored. So the KMS will use like a local enclave inside the flash memory region to store the secrets. And the ST-safe version of the code will use that external chip, the ST-safe, which is this external secure enclave, to store those chips off the flash or the MCU. And high-level boot flow when it comes to SBSFU is that there's a board initialization happening, so all the hardware layers are initialized, and then the ST-safe itself will initialize. ST terminology is a little bit confusing because they refer to ST-safe even in the KMS version when the ST-safe chip is not even used, but it just means that the secure engine is going to be starting up. And then they apply all the protections or check the protections. So all of those ARM features can be basically categorized into two sets of features. One is static, one that's when it's set on the device, it will stay there throughout power cycles and reboots. So those would be RDP, WRP, and proprietary code readout protection. And then there are all the runtime checks which have to be set by the boot process every time there's a power cycle happening on the chip. So these would be the firmware, the firewall, protection against like DMA access and a bunch of others. All the anti-tampering things would have to set during runtime, during boot. And then SBSFU uses a state machine. Initializes the state machine, which will be responsible for checking for updates, downloading, verifying, and then executing the user firmware. So the STSafe init bit, which was like the second step after the hardware has initialized, in the reference implementation is kind of just already left to the reader to implement. They have this like really rudimentary way of just putting the keys in the flash at a certain constant address and just loading it from there. But as the comment also says in the source code, this is not really secure, so it's already left to the developer to implement some safe way of storing the initial, or like loading the initial secrets, which is interesting. And then, yeah, the SBSFU state machine will start, which has all these features. Some are depending on whether STSafe is used or the local KMS version of the code is used. And each of these state machine steps will check that the previous check has, like the previous step has successfully completed, just so we avoid skipping over certain steps. And also all those like runtime and static checks that we talked about, checking like the RDP level, stuff like that, will be checked at each of these steps, just to make sure that no like time of check, time of use things have happened between these steps. So like RDP hasn't been downgraded since like downloading the firmware and before executing the firmware and things like that. And what's cool is that in the reference implementation, they already do side channel mitigations, like fault injection mitigations. So for example, these static checks might be executed twice after one another, just to ensure that fault injection is not messing with these checks. And yeah, so this is basically the part of the code that shows that all the previous steps have been completed before moving to the next one. So that was just a quick recap, or like a quick summary of how ST approaches secure boot. And now into the, let's go into a little bit more detail of our specific approach. So as I mentioned, we use this discovery kit, which is this thing. It's super useful because the MCU itself, the L4S5 is in the middle, but it already has on the PCB a bunch of peripherals that you might be using. So it has a Wi-Fi chip on the top left, it has USB ports on the board, it has flash memory, everything that you would need to start working with this specific chip. And it also has a lot of exposed headers, which is very useful when you're like playing with something and just want to get something working quickly. And on the bottom of the board, we can see that they also have an STSafe secure element on this discovery kit as well, which is great because we can then explore that part of the ecosystem as well. But we were a bit lazy, so we got this Nucleo-based extension shield, basically, which sort of just slaps on top of the discovery kit, and the circled chip, the thing is the STSafe that is also on the bottom of the discovery kit. But why we did this is because then we can do this. So we can just put the extension shield on top of the discovery kit, just using those headers. And because the headers are also exposed on top, we can just use our logic analyzer with just simple wiring, just plugging it into the right slots for the I2C bus and ground. So we have easy access to to the bus itself without having to trying to find the solder points or just having to mess with soldering at all. And the cool thing about the Discovery Kit is that it comes with the ST-Link debugger, which is ST's own sort of debugging protocol, and it supports source-level debugging using their own Xcube IDE environment, which is great. So you just plug in a USB cable into the board, the other into your laptop, and you have source-level debugging using GDB, which is just excellent when we were exploring these sort of things. I keep talking about this ST safe thing. The chip it's just that. It's a little really low powered chip. The hardware configuration is pretty black box for obvious reasons. This is what is the safest part of their ecosystem. All we know is that it has 6 kilobytes of configurable non-volatile memory. It has one-time programmable fuses as well to store secrets, and it communicates with the main MCU using the I2C bus, which is great for us because it is at X surface. Because a lot of the modern chips, like your iPhone, for example, will have a similar secure enclave, but that's built into the main MCU as well inside the die. So there's no easy way for you to intercept the communication between the CPU as it performs all these secure boot functions using the secure element. But in this case, it's an external chip, so it's great at X surface for us. There are some commands, don't really care about them, they support a bunch of things. It's a bit dry to go through them, but we did find a bug, which was great. So the little GIF here shows the code running, and then when we put on a malicious shield, which was going to simulate malicious access to the I2C bus, basically in a person in the middle style of attack. The code there will execute, and LEDs will start blinking, showing that malicious code has been executed. How that works is that when the MCU reads off the I2C bus, this is the main utility function, the hardware context bus receive function that's reads off the bus using preset length of data to be read into a buffer that is held in the by the CPU, the main MCU. So this part is fine. The length on the top is preset, not user controlled, nothing wrong there. But once the read happens, the driver basically will reset the length of the buffer based on the code received off the bus, which is user controlled. And then if that length received from the bus is longer than the response length previously set as a static, to 523 bytes in case of the SBSFU, a second read will happen because that will basically mean the ST-safe will tell the MCU that we have more data to send. So a second read will happen on the bus using the same function, but now the length of that read is going to be controlled by the attacker, which means that we can write past the length of the previously set buffer. It's a pretty straight-up memory corruption vulnerability. So in order to do this, we also wrote a little plugin that you can use with Sele Logic 2, which is the software for the Sele logic analyzers. So if you use this and you intercept I2C communication, you can just get an idea of what kind of commands are being sent through this bus and what are the responses and things like that. I have to note that this is only going to work in non-locked down production devices because ST-safe will encrypt communication in a properly controlled environment, in a production environment. But during just development, this can be a really useful tool to just intercept the messages and see what's running through the I2C bus. And then that's just a quick recap of the ST-safe ecosystem. There's still a lot to do. We mainly focused on the ST-safe, the STM ecosystem, and we mainly focused on the ST-safe chips, but yeah, there's still a lot to do, a lot to cover in the SBSFU packages as well. And then as an introduction.
Okay, yeah, so that's an overview of our work for ESP and STM. There are many other places where dragons be lurking for research topics. The SCP supports execute in place. There's also these co-processors which can run in deep sleep that might have access to memory that you can exploit. DMA padding, essentially everything in the list here is attack surface that we're currently exploring. And you'd probably have some luck if you looked into these areas as well. Our plans for the future include just a lot more auditing over these same devices, as well as even more. And some of the tooling that you saw in the talk today will also have some improvements and so on made for them.
Zoltan.
Speaking of the tooling, the repo that's on the slide will host links to a lot of the tools that you saw. So if you're interested in using them, feel free to check out the repository. It's not pushed just yet, but today I'll make sure that we get something in there. One final thing, since it was a collaboration project, one of the things that we realized is it was important for everybody to have a test environment that we could use to reproduce each other's work, or just to get stuck back into auditing when the time came back again. So we created essentially a bunch of Docker containers as well as dev containers that lets you essentially spin up these ESP and STM environments for code auditing and hacking. Just takes one command and then you're ready to go. So if you found anything in this talk interesting and you're inspired to either replicate the work or go off and do it yourself, you'll find essentially some tooling that makes that very easy to do. A lot of the work that sort of got us started here was sort of based on prior work, people who have done a lot of research into fault injection attacks, that first stage boot ROM attacks and so on, and had a lot of really interesting information that we were able to leverage once we got into the second stage bootloader. Just the one thing that I'd love to point out here is Travis Goodspeed. He's published this microcontroller exploits book just recently. It's an absolutely phenomenal book, very interesting read, so definitely check it out if you're interested in this sort of topic. With that being said, I think we're done. We might have time for questions, but thank you.